Okay, welcome back. So now we're on to another section, B.6.6. So B.6 is how to calculate limits. And B.6.6 is about something called the fundamental sine limit. And the fundamental sine limit is related to this really funky function that you see over here. So this is a funky function. It's the function sine of x divided by x. Here's what it looks like in Desmos. And the point about this function is it is a cool looking function. It's got squiggles, but it has this cool behavior at 0. If you draw the function 1 over x, you'll see that 1 over x, and let's do 1 minus 1 over x. So you'll see that the functions 1 over x and minus 1 over x are the envelope of this funny function. The blue function sort of lives in this envelope made of 1 over x and minus 1 over x. And that's because the sine function goes between 1 and minus 1. So if you do sine of x over x, that's like living between 1 over x and minus 1 over x. So that's not surprising. But the cool thing is what happens here near x equals 0. Because these purple and green functions, 1 over x and minus 1 over x, go to infinity. But the blue function does not. And that is what this section is about, is doing the limit as x goes to 0 of this funny function. I will say one other thing. This function has a cool name. It's called the sinc function. It's called the sinc function. There's even on the Wikipedia page for this thing, there's a whole Wikipedia page. And there's a funny little thing where it will play the sound for you. So here's the sound. Ready? You can't hear it, can you? Yeah, okay, maybe you barely heard it. So it's anyway, you can check out this thing. There's a whole Wikipedia page about it. It's a very important function. It comes up in all sorts of things. It's the first reference to it is in this book from 1953 on applications to radar. It's a serious boy function that is super important. What we're doing today is the limit as x goes to 0. Or the limit as theta goes to 0 of sine of theta over theta. And this is a classic 0 over 0. The top is 0. The limit as theta goes to 0 of sine of theta is 0. The bottom is just the function theta. Theta goes to 0 of theta. That's also 0. So this is a classic 0 over 0. So this is a type 0 over 0 limit and is therefore indeterminate problem. We cannot simplify to get rid of it. So far, all the 0 over 0s you've seen, you can just algebra them away. But this one, you really can't. So there's something funny going on. And looking at the graph, we can see from the graph, the limit is going to be 1. So the graph makes it totally clear. The limit, we're getting close to 1. The limit should be 1. And so this is the fundamental sine limit. It's a fact if you want. Fact. This limit equals 1. And you can use that limit whenever you're doing limits involving sine. You can use this limit. I do want to spend a couple minutes explaining why. Why is it 1? It's a very cool thing. So why is it 1? And I'm going to prove it using, let's prove it. We're going to prove it using geometry. So you remember the definition of sine. What was the definition of sine? Sine was you take the unit circle and the sine of an angle is the height, the y-coordinate of what you get when you do an angle theta. So you do an angle theta, and the height you get is sine of theta. If you remember the definition of radians, what is the definition of radians? The angle theta means that the length of this curve is also going to be theta. And you can see it visually from the picture. If the height is this vertical component, this blue length, and the curvy part is length theta, then definitely the sine of theta has to be less than theta. Sine of theta is the vertical part, this blue length from here to here, and theta is this curvy length. So sine of theta is definitely less than theta. If sine of theta is less than theta, we're talking about positive angles here. I can divide both sides by theta, and what do I get? That means that the sine of theta divided by theta, that's what we care about, is less than 1. So it's less than 1. On the other hand, you can also draw, in the unit circle, you can draw the tangent of theta. And the tangent of theta is this line that goes like this. It's a vertical line that starts at x equals 1, so tangent to the circle, and it goes up to until where it hits this the ray coming of angle theta. And you can see from the picture that theta, the green part, theta, the green part, this part, is less than the tangent of theta. So you can see that visually from the geometry picture. And if theta is less than the tangent of theta, well, tangent is sine over cosine, you can rearrange this equation because we're looking at positive angles here. That means that the cosine of theta is less than the sine of theta divided by theta. And if you combine these two facts, so one fact said that the sine of theta over theta was less than 1. The other fact said that the cosine of theta is less than the sine of theta over theta. If you combine them, you get this whole thing, that the sine of theta over theta, that's the function we care about, that is sandwiched between, or squeezed between, 1 and cosine. And you can see that on Desmos. Let's look at what this looks like on Desmos. So here's our function. And we're talking about two functions. There's the function y equals 1. Y equals 1. Is that a function? Okay, I gotta tell Desmos I want to do y equals 1. Y equals 1. So is it true that the blue curve, sine of x over x, is it always less than 1? Yes. It's always less than 1. And then the other function was cosine of x. Y equals cosine of x. And okay, we were only doing things in the first quadrant. So maybe I should say y equals cosine of x, and only for x less than pi by 2. We were only doing the first quadrant. And bigger than 0, positive values. Negative pi by 2. Okay, so this is what we have. That's not what I want. I want this. Okay, so the blue function is what we care about. The sinc function, sine of x over x. We have proven, using geometry and that picture of the unit circle, that the blue function is squeezed between the black function, which is a constant, y equals 1, and this red function, which is cosine of x. And these two functions, they squeeze the function in so that you can see that the function has no choice but to have a limit of 1. So when you have a function and you can squeeze it between two functions that you know the limit of, we know the limit of 1 is 1. We know the limit of cosine, that's the red curve. The limit of cosine is also 1 by continuity. And so we know the limit of the red and the black, and it squeezes the blue into what we want. This idea is called the squeeze theorem. So the squeeze theorem, if f is a function which is squeezed between a lower function and an upper function, you can give them a name. The lower function was the red function in the picture, L, and the upper function was the black function, U. L and U for lower and upper. So if f is between L and U, and the limit of L is something, and the limit of U is the same something, capital L, and they're both equal, then the limit of the middle function has to be the same thing. So this is called the squeeze theorem, and it is a way to prove limits, things like 0 over 0 limits, when you can't simplify or do anything else. You can look for an upper and a lower function that squeeze the thing you're looking for and prove it that way. And that's what we've done with sine of x over x. So here's a full proof. Here's a proof. Limit as x goes to 0 of sine of x over x. The limit is 1. That's a fact. That's the fact we're trying to prove in this chapter or talk about. And here is a proof. Here's how the proof went. By geometry. By a geometry. That was the thing in the picture. Sine of x over x was less than 1 and was greater than cosine of x. That is what we proved using the unit circle. Okay, so that was true. Also, the limit as x goes to 0 of cosine of x was equal to 1, and the limit as x goes to 0 of 1 equals 1. So the limit of these two functions, the one over here and the one over here, they both happen to be 1. Therefore, by the squeeze theorem, So the squeeze theorem, you can think of it's like one of the limit laws. It tells you as long as you have the right conditions, you can get the value of the limit you want. So what are the right conditions? We need a squeeze. We need the function we're looking for. It needs to be between two functions. That's exactly what we have with sine x over x. It's between cosine and 1. We need the limit of the two squeezy guys, the upper and lower guys. They need to be the same, and they need to both exist. In this case, it works. They're both 1. So by the squeeze theorem, we have all the conditions. Therefore, by the squeeze theorem, the limit as x goes to 0 of sine of x over x equals 1. That's it. So you can think of the squeeze theorem as like another one of the limit laws. It's a limit law that works when all the other limit laws fail you. It's like some kind of like epic action movie. Okay, that is the squeeze theorem and the fundamental sine limit. And the rest of the section is on how you use the fundamental sine limit to do some limits. So that's what I'm going to do. And in fact, you won't get any test questions that ask you to prove this, but you will need it in later math courses. So it's good to know the squeeze theorem for later math courses, even though the thing we're going to be asking you are examples like this, where you can just use the fact that the fundamental sine limit works. So you can take it as a fact and use it. That's what we're going to do in the rest of the section. So here we go. Evaluate the limit 5 sine t over 2t. And just like all the other limit laws, what you want to do is massage this until it looks like what we know. And in this case, I see there's a factor of 5 over 2, and then there's a sine t over t. And I know the limit of sine t over t, that's 1, that's the fundamental sine limit. The 5 over 2 is multiplying that. So by the times limit law, this is equal to 5 over 2 times the limit as t goes to 0 of sine t over t. This is the times limit law. Or if you want, it's the times limit law and also the fact that the limit of 5 over 2 is 5 over 2. So this is 5 over 2 times 1 by the fundamental sine limit. By fundamental sine limit, FSL. Fundamental sine limit, which is 5 over 2. Okay, here are some harder ones. They get harder. What about this one? Limit as x goes to minus 1 of sine squared of x plus 1 over x plus 1 squared. And what you can write with this one is you can do the limit as x goes to minus 1 of sine of x plus 1 over x plus 1 squared. That's what it is. We're squaring the top, we're squaring the bottom. You might as well write it in a bracket and square both. And now we're in perfect shape. We can apply the substitution rule. So by the substitution rule, if I set u to be the sine of x plus 1 over x plus 1, then the limit as x goes to minus 1 of u, that's exactly what we're doing, is the limit as x goes to minus 1 of sine of x plus 1 over x plus 1, right? So I'm doing a substitution rule, noticing that this whole thing in the bracket is like a u value. The limit as x goes to minus 1 of sine of x plus 1 over x plus 1, that's the same thing. You do another substitution. We're doing a substitution inside a substitution. Let's call it t. This is t goes to 0. If I make t be x plus 1, then as x goes to minus 1, t will go to 0. And this will be sine t over t, which is 1. That's the fundamental sine limit. So the point is, the thing inside the brackets is converging to 1 as x goes to minus 1. The thing in the brackets is what I called u, and I've shown that the limit of u is 1. So this thing is equal to the limit as u goes to 1, u is going to 1, of u squared, right? I've replaced the thing in the brackets with u, so I have u squared, and this is 1 by continuity. So the squared function is continuous. So this whole thing, I did it with substitution rule, doing substitution rule twice. Let me show you another way to write the same exact thing. You could have written, so okay, let me copy this stuff over. So this is the limit as u goes to 1 of u squared equals 1. Another way you could have done it, which means exactly the same thing, you could have just taken this limit and written that this is the limit as x goes to minus 1 of sine of x plus 1 over x plus 1 squared. So how did I go from this line to this line? What I did is I took the squared function and I moved it from inside the limit to outside of the limit. And that is okay because it exactly means a substitution rule. This is exactly a substitution rule. It's a substitution rule where this thing is the u value. U is the whole thing, the limit as x goes to -1 of sine of x plus 1 over x plus 1. This is what the u value is going to. So this is the, maybe I should say like u, the limit of u equals this. Let's write thing that u converges to, u goes to, is equal to this. So it's okay to move limits in and out as long as the function is continuous. And really what we're doing is exactly a substitution rule with this limit. That is exactly what we did over here. So I think personally for me, in my head, what's going on is the first way I showed you, but some people just do it directly doing this other way, and that's fine too. I would say it's a substitution rule with this thing, and I would say also the function u squared is continuous, right? And the function u squared is continuous. Because the function u squared is continuous, you can get the limit by just plugging in, so it all works out. So that's one way to do it, is doing this kind of thing, moving the squared in and out, which kind of does a lot of steps all at once, which maybe is confusing for some people. Or you can do it in several steps, slow it down, and do it really properly. The nice thing is about doing it properly and slowly is it will always work, whereas doing this fast way only works if it's sort of simple. So I like the first way I showed you better, but some people do it the other way, so it's good for you to see. Okay, here's another one. The limit as x goes to 0 of sine of 3x over sine of 2x. And this is one where you sort of need to make it the things appear that you want to appear. So what I'm going to do is I'm going to wish for, instead of having a sine of 3x and a sine of 2x on the bottom, I'm going to wish upon a star that it was sine of 3x divided by 3x. And then instead of being sine of 2x, it was 2x divided by sine of 2x. Because I know that if I had those things, then I could apply the fundamental sine limit. So I'm going to wish upon a star that I had these things. Of course, I don't have these things, but what I can do is I can multiply by 3x over 2x at the end over here. And now this thing is exactly equal to what we had before. So I've sort of creatively manipulated this thing to make what I want appear. I've made the things that I want appear by multiplying and dividing by 3x and 2x in the right spots. And if you do it this way, a nice thing happens. One nice thing is that the x's cancel over here. So the last bit is just 3 over 2. And these two middle bits are exactly the fundamental sine limit. They're u substitutions of the fundamental sine limit. This one is a u substitution with u equals 2x. This one is a u substitution with u equals 3x. But in either case, the u values are going to 0. So this whole thing, by the times rule, this whole thing is going to be 1 times 3 halves. And you could say, since the limit as x goes to 0 of sine of 3x over 3x equals 1, and the limit as x goes to 0 of 2x over sine of 2x equals 1. Those are the two limits I used in the middle, and those two limits are exactly the fundamental sine limit, but with a u substitution. So the final answer is 3 halves, and we're combining all sorts of limit rules here. So if you're rusty on your other limit rules, this is probably going too fast. You're going to need to slow down and do it slowly. But these middle limits are just fundamental sine limits with a u substitution. The final thing is a 3 halves. You combine it all by the product rule. 1 times 3 halves is 3 halves. So that's the final answer. Okay, there's one more. It's the last one. The limit as theta goes to 0 of 10 theta over tangent of 3 theta. And tangent, we know, tangent is the same as sine over cosine. So simplifying a bit, this is going to be sine of 3 theta times cosine of 3 theta. And cosine of 3 theta is going to 1. So this guy on the end here is kind of boring. He's not doing anything. He's going to be converging to 1. The interesting part is 10 theta over sine of 3 theta. So why don't we make a 3 theta appear, and we'll write it like this. We'll write this as I want 3 theta. This is what I wish upon a star for, times cosine of 3 theta. tan theta, I had 10 theta, now I replaced it with a 3 theta, so to be honest, I better bring it back and write 10 thirds. Okay, and just like before, I have 3 parts. The middle part is 3 theta over sine theta. This is going to be converging to 1, and it's a u substitution with u equals 3 theta of the fundamental sine limit. That middle part's going to be going to 1. 10 thirds is 10 thirds, and the cosine of 3 theta is also converging to 1. So this is going to be, by the times rule for limits, this is going to be 10 thirds times 1. The cosine is up 1, and you could write, since the limit as theta goes to 0 of 3 theta over sine 3 theta equals 1, and that's a u substitution of the original fundamental sine limit. Okay. So the final answer here is 10 thirds. Okay, so those are some examples of things with the fundamental sine limit. It's another ingredient that can possibly come up among the set of things you can see in limits. And it has a cool proof. It's a funny function, but you can do this cool squeeze theorem proof of why it works. This squeeze theorem thing comes up in all sorts of later math courses. So this is kind of like a teaser. If you're into this kind of thing, you'll enjoy the later math courses. Okay, bye.